Okay, everyone, I'm going to get started because we have so many materials to go through. To save some time, I did this, and let me see if I can accomplish doing this. Okay, and I do done, and then you can see this, and hopefully it is recording too. Okay, so first of all, can any of you tell me what is a reaction? Anyone? Yes? Yep. Can you say it louder? Oh, okay, sorry. So anything that I'm telling you, I'm going to ask explicitly in the exam. So that's why I'm emphasizing on the definition. So anyone? Yes?
Is it a chemical change, a full chemical change?
Yes. So basically in a chemical reaction, we have like one or more substances that they transform to other substances. And can any of you tell me what are some signs that we have chemical reaction, some evidence? Yes?
For a chemical reaction, state change, so like a change from like liquid to gas.
Yes.
Color change.
Yes. Yes.
Like a little heat.
Yes. What else? Yeah.
Light emissions?
Yes. Is there anything else? That can be, yes. I mean, it wasn't explicitly stated in the book, but yes. And then we can also have like heat absorption, right? Heat absorption, heat emission, light emission, like color change, formation of solid, formation of gas. All of this can be a sign or evidence that we have a chemical reaction. But does it necessarily mean that if we have gas formation, we have a chemical reaction? So I'm telling you, I give you in the test that is formation of gas always a sign of a chemical reaction, true or false? Exactly. What is one example? Can anyone tell me? Yes?
Like boiling water.
Exactly. So we don't have chemical reaction. We just have like water in liquid state converted into liquid in gas phase. And then we talked about aqueous solution. So can anyone just like from the board or like, from your memory, tell me what is an aqueous solution? You can just read it from the board too. I don't mind. So can anyone tell me?
A homogeneous mixture of a substance with water.
Yes. So exactly. So basically, if you have like, if you dissolve, sand in water, or not dissolve, if you like put some sand in water and then stir it, is it a aqueous solution? So why did you say yes?
Because it's a substance with the water.
But is it homogeneous? What is the definition of homogeneous?
They're really mixed.
Exactly. So when you can distinguish the sand and water, that is not homogeneous, that's heterogeneous. So for instance, if I have like put some salt in water, stir it, and then imagine like you have like a big cup of hot tea. I mean not tea, probably won't put like salt in hot tea to drink. But imagine you have like boiling water, and then you put 1 spoon of salt in it and then stir it. Would that be an aqueous solution? Yes. Exactly. Why? Exactly. So this is aqueous solution. And then we talked about electrolytes, specifically strong electrolytes. So can anyone tell me, whether from your memory or from the board, what is a strong electrolyte? So what do we call an electrolyte? You can just read it too and then just tell me. I just want some, evidence, like a chemical reaction. I just want to know some evidence that you are learning, and that would be like you repeating. I hear your voices. So what is an electrolyte, strong electrolyte?
Substances that completely disassociate into ions and solutions are called strong electrolytes.
Exactly. So for instance, if you have sodium chloride, you have like Na plus cation and Cl minus chloride anions. So if you have those, if you put salt in water and then stir it, you won't be seeing salt anymore. If you have a microscope and then you look at them, you see sodium ions and chloride ions, Na plus, Cl plus. It means that they separate, they dissociate in water, and they can conduct electricity because, ions, and, as we go further, we see that some ionic compounds, when we dissolve them in water, they dissociate, and these ions can conduct electricity because they have charge. So we call these strong electrolytes. So what do we call strong electrolyte solutions? Anyone? Basically, when we dissolve these, yeah? What's that?
Water plus sodium chloride.
Yes. So basically, when you have like these ions in water, and then you dissolve them and they dissociate, you call them strong electrolytes, and the solutions containing those ions, you call them strong electrolyte solutions. And then something that, is stated in your book and is really important is that when you dissolve polyatomic ions, so basically when you have salts or you have ionic compounds and you dissolve them in water, the ones that dissociate and they are soluble in water, if they contain polyatomic ions, the anion or cation stays as such. For instance, if you have like, NO3 minus, can anyone tell me what is the name of these polyatomic ion? Yes. So if you dissolve them, you won't be seeing nitrogen and oxygen itself. You just see nitrate ions in the water. Any questions so far? We're just like reviewing from previous session. Any question? Everything's clear? And then we had like two definitions, a soluble compound and insoluble compound. Can anyone tell me what do we call soluble?
Something that can be dissolved in water.
Exactly. So what is insoluble? Exactly. So if they can be dissolved in water, we call them soluble. If they can't, it's insoluble. And then we mostly talk about water, solubility in water, but the general definition is that, if we have a specific substance that can be dissolved in a liquid, we call that compound soluble in that specific liquid. But in this chapter, mostly we talk about solubility in water. Okay, so now let me go to the second image. And then I should press done so people at home can also see this. Okay, so something that is really important, and again, everything that I'm talking about, I'm going to ask you in the test, so pay full attention. So we talked about strong electrolytes and strong electrolyte solutions. And one thing that I told you is that the strong electrolytes are really good conductors of electricity. So if we have like a strong electrolyte solution, it can basically turn on a lamp if we connect it, if we put it in the solution. Why? Because we have cations and anions in our solution that they have like charges, and then they can conduct electricity. So pure water, if the water is completely pure and doesn't have any other electrolytes in it, it cannot turn on a lamp. So I'm going to give you, for instance, a lamp that is on and it produces light, and tell you which one statement is correct, or which solution does it represent. And then you know that if we have like sodium chloride solution or AgNO3, can anyone tell me what is the name of this compound, AgNO3? Yes? Silver nitrate. So why didn't we say silver 1 nitrate? Isn't silver a transition metal? Shouldn't it be like in parentheses 1? What's that?
You don't have to write the line, it's
So yes, because, so it's not necessarily, it's not because it's 1, it's because it belongs to the table that is just like the cations that only can have 1 charge. So basically, yes, what you said is right, because it only have like 1 sort of charge, but don't confuse it with 1, because we had like that mono in molecular compound at the beginning of the compound. For instance, CO, we don't say monocarbon monoxide, we say carbon monoxide. So this is different from that. It's not because of the specificity is 1, but because it only can have 1 type of charge. And you know how to name AgCl? Yes, and the same thing here. The table that in your book, and now all of you have access to the book, that table that has like the cations that only have 1 charge is really important. And I'm going to ask you, I asked you in quiz, and I asked you in exam too. So remember, Ag, silver only has 1 charge. What was the other ones that had only 1 charge?
aluminum.
Yes, and what was its charge?
It's under 23.
Can anyone else tell me? Aluminum? No. 3. Yes. So aluminum is +3. It only has 1 charge. What else?
Zinc.
Exactly. And what is its charge? Exactly. And then what other groups in general had like only 1 charge, 1 sort of charge?
The alkaline earth.
Exactly. So remember those. And those are really important for your exam. And, okay, going back to this chapter, you see that everything is really interconnected. If you don't know previous chapters, you cannot progress with these chapters, So make sure that you learn everything well. And then we talked about ionic compounds, and we said some of them are soluble in water, some of them are insoluble in water. And we said there is not exactly a specific mathematical rule for compounds in general that we say whether they are like soluble or insoluble. But for ionic compounds, we have like some empirical observations, and based on those, some scientists made some rules that we know that, okay, if we have these types of ions, and if they dissolve in water, we have like they are soluble in water. And if there are like these sorts of ions, they are insoluble. So for instance, AgCl is insoluble in water. So if we have like silver chloride, AgCl, in water, and if we like stir it, we will see AgCl in water, as such. It's as if you have like some AgCl salt in water, and then you see that they don't dissolve. So if you connect it to a lamp, you won't see any light because it's not a strong electrolyte solution. And then you see that here in the picture on the bottom, we have like AgNO3 minus. So I'm going to teach you the rules like in the next picture, that you see that if you dissolve those, if you have like AgNO3 put it in water. You stir it, they dissolve. So you see cations and anions. But, and in general, you see plus charges and minus charges, cations, anions. And then I can give you the beaker on the right with plus minus and say which one of these salts, if I dissolve in water, represent this picture. And then you see, you can say that, okay, AgNO3 and NaCl both dissolve in water, so they dissociate. So it generates the beaker on the right. But this beaker on the bottom of the page, that is just like a cube crystalline structure, that represents a salt, an ionic compound that we stirred in water, but it didn't dissociate. It means it's insoluble. So it would be AgCl. So kind of like try to learn these concepts well. And then I'm going to go to the third picture, and I press done. Okay, so this is something that I just told you. We don't have an easy way to just look at, mathematically or with a universal rule, say what is soluble, what is insoluble, but they are like table 7.2 and figure 7.7 that summarizes some rules. So you will use those rules to answer questions in these sections. And here, I kind of like, your book was like kind of explaining the table, so I wrote these down too, so you can kind of see how you should read the table. So for instance, if you have a compound that it has lithium ion, you can say that it is soluble in water without any exceptions. So if you see an ionic compound that has lithium, you can be sure that it's soluble. So it doesn't matter whether you have like LiBr, LiNO3, and then in the next picture I have its name too. So can you just, without looking at your book, tell me how would you name LiBr? Yes. Can anyone tell me what is LiNO3? Yes, lithium nitrate. And what is Li2SO4? Yes, lithium sulfate. LiOH? Exactly. And Li2CO3? Lithium carbonate, right? Yeah, sometimes math can, prevent me to hear well what you're saying, but lithium carbonate. And then, if a compound contains Li plus, then we call that lithium cation or lithium ion, it is soluble. And also, we have like similar rule with anions. If a compound has NO3 minus nitrate, it is soluble. For instance, if you have like AgNO3, PbNO3 2, and anything that has like NO3 minus, they form strong electrolyte solutions. Any questions so far? So you have a table in the book that I'm going to show you. So let me just like show you this table. And I also wrote it down. Okay, you see this table? You should memorize this. And now you have it gets easier. When you solve examples, it seems complicated, but it's not. So right now you learn that if you have like lithium, sodium, potassium, ammonium, anything that has these, no matter what, they are like soluble. Any ionic compound, of course. And then nitrate, acetate. These are like all soluble and they don't have any exceptions. So let me go back to this that I was showing you. And now let me go to this picture. Okay, now here, because I asked you in your quiz and I'm going to ask you in your exam, and more importantly, you need this for the chapter that I'm teaching now, you should know its name, their names well. So lithium bromide, lithium nitrate, lithium sulfate, lithium hydroxide, lithium carbonate. And I told you for the exam on Friday, you don't need to memorize polyatomic ions. I'm going to give you the table. But for this chapter, as you go through, you need to know this, especially the ones that we use a lot, like nitrate, sulfate, hydroxide, carbonate, and then when you solve examples, these become easier. So AgNO3, silver nitrate, or PbNO3 too. Can anyone tell me the name? Lead nitrate, you said?
Yeah.
So lead is among the elements that can have multiple charges, right? So what do we call it? Exactly. So, and then sodium nitrate. Why didn't I say sodium bond nitrate? What's that? Exactly. So its charge is fixed, it won't change, and then strontium nitrate and then calcium nitrate. So there is another thing, when you want to read your table, and I listed the table in the next slide, So in general, compounds that containing CO3 2- carbonate ions are insoluble, but they can have exceptions. And let me go through next slide. So you can see what I'm saying. I also included these names. Okay, so I said CO3 2- carbonate. Most of the things, most of the compounds or like ionic compounds that it forms are insoluble. And I included the names so, it helps you for your exam. For instance, copper is among the elements that have multiple charges, so you write the charge in parentheses. But calcium, strontium, they just have fixed charges, invariant charges, so you don't write the 1 or 2 in parentheses. And then FeSO3 is like iron 2 carbonate. So these are insoluble. So we said that in most cases, solubility rules have exceptions. For instance, in this case, CO3, okay, and I think here I made a typo. It should be CO3 2-. Let me see if I can. Yeah. Let's see. Okay. That worked. CO3 2-. So they are insoluble, but I told you lithium, sodium, potassium, ammonium, those are soluble no matter what. So if you remember that, you remember that if although carbonate is insoluble but forming, if we have them in an ionic compound with lithium, sodium, potassium, ammonium, it would be soluble because those ones are soluble without any exceptions. Is it clear what I'm saying? Does it make sense? Yes.
So if you have like lithium carbonate or sodium carbonate, those are all soluble even though they have carbonate in them?
Yes, they would be soluble, although they have, in spite of having carbonate, they are soluble. So if you remember lithium, sodium, potassium, ammonium, they are soluble no matter what. Even if they have anions or like cations that they form insoluble compounds, since they are soluble, you would be having soluble compounds. And then gonna go
So are these things that we need to know for exam 4 or for the exam?
for exam 4. So naming them you should know for exam 3 because I asked you in the quiz and in the exam 2. And then I'm going to give you polyatomic ion table, so it won't be that challenging. But for the exam 4, you should, know this. So this is your table that I just wrote here, so we can talk about them, but you have them in the table 7.2 that I mentioned. So this is solubility rules. If you have lithium, sodium, potassium, ammonium, and I wrote down their names too for the sake of your exam 3. And that's why I'm really emphasizing on those, because they are really important. So they have no exceptions. If you see, lithium, sodium, potassium, ammonium ions in an ionic compound, and I ask you whether or not they will be soluble in water, without any exceptions, they would be soluble. Any questions? And then, if you have nitrate or acetate, as I showed you in the book like some minutes ago, if you have an ionic compound that has these two anions, you would be having, soluble compounds without any exceptions. And this, table is for soluble compounds in general. On the right, I have like the exceptions. Any questions? Okay. So if you have chloride, bromide, iodide, and you have like a table in chapter 5 that is really important, and table 5.6. Here is really important for your exam. Like, if you have like, F minus is fluoride, Cl minus is chloride, Br minus is bromide, I minus is iodide, and then basically anything that is in your group 7A here, they form one charge, and then negative charge. And then if you have like oxygen and sulfur, you'll be having like iodide oxide. They have charge of plus, they have charge of 2, and then they are anions, so minus 2. And then nitrogen is nitride 3 minus. And remember, you had also in your polyatomic ions, you have like nitrate and nitrite. So don't confuse those names. And this table, remember table 5.6, the thing that I just mentioned. So, let me go back to this. Okay. So if you have chloride, bromide, iodide, you'll be having a soluble solution, but they have exceptions. So what are the exceptions? One was like Ag. Do you remember when I told you AgCl in the first example that I said in the previous slides, in a sense? It was like insoluble. And also Hg2, 2+. Can anyone tell me why do we call that mercury 1 but not 2? Yes? Anyone? Yes? Exactly. We have like 2 mercuries and then 2 plus charges. So it's as if each of them has 1 charge. Right? Does that make sense? We have 2 atoms with 2 plus charge. So it's as if each of them has 1. So it's like we call that mercury 1 and lead 2. So if you have like these, so silver, mercury 1, lead 2 are exceptions for like chloride, bromide, iodide. And also sulfates. If you have your compound has like SO4, 2 minus, it would be soluble, and these are exceptions. Calcium, strontium, barium, lead 2. And if you remember lithium, sodium, potassium, ammonium, nitrate, and acetate, the ones that have like no exceptions, the other ones, as you go through examples, you learn how to use them and then you become good with them. At first, maybe it seems overwhelming, but the way to memorize this is solving problems and examples. That's why I try to make sure that you have access to your book. You can go work through quizzes. You can have like worked examples that you can solve problems. You have videos that explain to you the solutions. So when you go through problems and then solve problems, you can learn these better. And now this is basically part of the table has like insoluble compounds. So basically if you have like these ions, they are mostly insoluble. So OH minus, we call them hydroxides, or like S2 minus, we call those sulfide. And then you should know sulfide, in the exam, in this exam on Friday, I give you hydroxide, but S2 minus is in the table that I just showed you, and you should know that. So if you know lithium, sodium, potassium, ammonium, I told you to memorize them. Those are always soluble, so those are exceptions to these. So if you have those, you would be having soluble compounds. And then specifically for sulfide, if they pair with calcium, strontium, and barium, they form soluble compounds as well. And also for OH minus, basically if hydroxide pairs with calcium, strontium, or barium, the compound is slightly soluble. And then your book mentioned that for many purposes we consider them insoluble. So again, instead of the first step for you is to go to the table, study that, kind of like trying to memorize it. But you learn when you go through worked examples, and try to solve as many problems as possible. And I'm going to post for you for this chapter some examples as well, so that you can walk through them and then learn these better, probably for extra grades. Any question about that? I know maybe you don't, you didn't memorize this by just looking at them, but in the sense of rationale of how if you have this table, can you recognize what ionic compound is soluble or insoluble? Do you know how to look at this table? Any questions so far? Okay, and now let's walk through some examples. So, AgBr. Can anyone tell me if it's soluble or insoluble? Why? So, if you remember, if we have bromide, most of the time we have soluble compound, but Ag plus is an exception. So to have you let me do this. So I give you this table. Let me see if it's better on or off. Maybe. Okay. So I'm going to ask you. So look at CaCl2. Can anyone tell me, is it soluble or insoluble? Why? Maybe just move this here. I don't have to hold this. Okay. CaCl2. Okay, why? So you have Cl minus, that is soluble, and then you go through exceptions. Are they Ca calcium here? No. So as your friend said, it is soluble. What about Cus? First of all, can anyone tell me the name of Cus? What is Cu? Yes. What is S? Or like what charge does it have, first of all? -2. And then, you can, in your head, Cu had the charge of, 2. I mean, it has like variant charges, but one of them is 2. So since we don't see any number is Cus, they should cancel each other out, right? So it should be like 2 and 2. So how do you name Cus? Copper sulfide, but since copper has variant charges, we should say how many charges it has, right? Exactly. So now, based on this table, can anyone tell me if Cus is soluble or insoluble? Soluble? So here, first, when I give you an ionic compound, in your head you say, okay, Cus, it should be Cu2 plus S 2 minus, right? So here I don't have a rule for Cu2 plus on the left specifically, but I have rule for S2 minus among insoluble compounds. And then here I say, okay, Cu, is it exception? Is it? So S2 minus is insoluble. And it mixed with Cu2 plus. So I say, okay, S2 minus is insoluble. Unless, it mixes with one of its exception. Is Cu2 plus among the exception? No, right? So Cus would be insoluble. Let's go through another example. For instance, if you have like iron 2 sulfate, which is like FeSO4. So if you have, if you have FeSO4, okay, my pen isn't writing, but if you have FeSO4, by looking at the table, can anyone tell me if it's soluble or insoluble? Why? FeSO4. So the first thing you do is that you write this as Fe, 2 plus SO4, 2 minus, right? And then you go to your table 7.2. So do we have a rule for Fe2 plus on the left? No, right? But we have a rule for SO4, 2 minus, right? Which is most of the time soluble, but it mixed with Fe. So is Fe an exception? No. So it would be soluble. Going back to this, and I included some other examples too for you to walk through. Okay, now you see this kind of like distorted. But, so this is how you see if a compound is soluble or insoluble. But for the sake of your exam on Friday, can you tell me the name of NH4Cl? Yes, say. Exactly. And then, is ammonium chloride has a metal in it? No, but is it an ionic compound? Yes. Why? Exactly, because the definition of ionic compound is a substance that has like cations and anions. Not necessarily metals and nonmetals, but except ammonium, most of your cations are metals. So pay attention to those. And also like PbNO32, what is the name of that? PbNO32. What is NO3? Exactly. So kind of like try to, memorize this. Or rather know how to do this. Okay. Now, let me see. So these were review of the previous session, basically, which took me almost most of the time of the class to talk about. But I hope you now have a good understanding of solubility, aqueous solutions. So can anyone tell me what is a soluble compound? Exactly. Dissolve in liquid, yes. So in general solubility, you can dissolve a substance or compound in any liquid. So what is aqueous solution? Exactly. So when you dissolve something in water, basically forms a homogeneous mixture. Anyway, now next part is precipitation reactions. Reactions in aqueous solution that form a solid. Can anyone give me an example of a precipitation reaction? Or describe to me a precipitation reaction.
Solid precipitate forms upon mixing two aqueous solutions.
Yes, exactly. If you have two aqueous solutions and then you mix them together and then you see a solid being formed, you call that a precipitation reaction. It's like the example that I gave you at the beginning of the chapter about the laundry detergent, that if you have laundry detergent has a specific material in it that when it reacts with magnesium and calcium in hard water, separates them, so basically forms a solid and make them precipitate. So basically, in your laundry detergent, you have sodium carbonate. And then, can anyone tell me the formula for sodium carbonate? NaCO3. And then also, so when you want to write this chemical formula, write sodium first and then it's Na plus, right? And carbonate is CO3 2 minus, right? So this has the -2 charge, the net charge is -2, here is +1. So how many sodium ions should I have to basically have this compound neutralized? Exactly. So this would be sodium carbonate. And then if you have questions about naming ionic compounds or naming molecular compounds, naming acids, or anything else, just ask me, send me an email, or come to my office hours. I gladly explain them to you because you need them for your exam. So they react with, for instance, magnesium ion, and they form. So how you write these type of reactions, when you have precipitation reactions. This ion here, it reacts with this anion here. So basically cation on the one of your substances, one of your reactants, as we mentioned, reacts with this carbonate. So you will be having Mg and CO3. And then when you want to write the chemical formula for that, you say, okay, Mg is 2 plus, because you know that table that I just mentioned is like in the group 2. And then CO3, 2 minus. So you don't have to change, it's already neutralized, right? Is it clear? So you just write MgCO3 plus this sodium itself, Na plus. So what you did, you have like, and I'll give you more examples, in a minute. But when you want to write this type of reaction, your cation from one of the compounds react with the other anion, or kind of like, you write them together, and then the other cation from the other compound with the other anion. In this case, we don't have another anion. Is it clear how we wrote this? And then if you remember now, so basically you have like Na2CO3, and based on your solubility table, you know that these two form an aqueous solution, plus Mg2 minus aqueous, because the ions would dissolve in water, and then it forms MgCO3, which is solid, plus Na plus, which is again aqueous. So do you remember what was balancing an equation? So now I wrote a chemical equation, and why would I need to balance it? And what was balancing an equation? So we use neutralization mostly for charges, but you're close. Basically, we said based on the law of conservation of mass, we should have the same amount of mass, the same amount of atoms on each side of the equation. So if we have like 2 sodium on the left, we should have 2 sodium on the right. And if you remember, we said that if we have like atoms that are by themselves, or if we have like elements that, just by themselves, it can be just like O2. Still, oxygen is like molecule, but it's, just one element. We do balance them at last. So in this case, I start first with which part of this, and the other thing that is important, when you have like ionic compounds or salts, as I said, by the same rationale that when they dissolve in water, you won't be seeing carbon and oxygen by themselves. You see carbonate. You see CO3, 2 minus. They remain intact. When you want to balance them, you kind of treat them together too. If you don't do that in your exam, you would be having lots of trouble because you're like panicking, balancing carbon and then oxygen, and then it's just like not needed, it would waste your time. So here CO3, Mg, Na. So which one of these units basically I would balance first? So, yes and no. In the sense of this problem is easy, so yes, you do Na. But based on the rules, you do Na and Mg last because they are by themselves, right? So you would start by carbonate, but since it's already balanced, you go to Na. So you're right, So CO3 is like 1, and then Mg is also, in the sense of number of atoms, is 1, and then as your friend said, you added 2 here. And then your charges are also balanced because you have like 2 multiplied by +1 and then +2 here. So if right now you don't have to stress out about the charges. We talk about them later. But right now, this is a form of precipitation reaction that you have 2 aqueous solutions and then you see solid. And I just wanted to show you real quick, I told you, I posted that you gain 5 more points if you do the quiz on chapter 5 and 6 by the end of the day on Tuesday, basically 11 p.m. tomorrow. And then if you didn't set up your book on BB Learn already, I encourage you to do that because it's just like easy grade, 5 points you can gain. And then when you do that, you see that how beneficial it is for you to learn the material. Yes? Okay, so you have the book, right? So now you can go through the same thing here. Yeah. This is the here. And then this is the chapter. Yeah, and then it has like exam, go to chapter 5, exam prep. Yeah. You see it's about the something. It's just like what you were doing before, you give me the scantron at the beginning of the class, but I also need the solutions because I want to make sure that everyone solve the problems themselves. And I see, what are the common mistakes, errors to try to attack them. But if you can, give them to me separately, not staple them together, because I'm going to give you back the solution or ask you to come pick it up from my office,
Do the chapter quizzes right online.
Oh, that one, when you're done, just take a screenshot and then send them to me. It just tells that how many correct, how many incorrect you have.
Does it matter how many you get correct and how many you don't?
Honestly, you can just go read the solution and then do the quiz again. I'd rather you just retake it if you have mistakes. So I have a student that they had half correct wrong. I asked them to do it again. So.
Thank you.
Of course. Yes, just give me 1 second. I try to, oops. Sorry.